Last time we talked about something about the how the wage system call and existing call they actually come in pair, right? Because the wage system call actually waits for termination of the partner. The partner is the child, okay? So that's why two guys is using two different system call, and they kind of need the communication. Now, last time we started the moment that I talked about there is the solving process, and the solving process is actually a process without code. Okay, without memory, without code, just a hollow body here. Somebody already asked me a question, hey, why there is a zombie? Okay, so actually the zombie is a placeholder holding what? Holding the PID, okay? And not just the PID. Let's say that I want to know whether this child has run for how many times before a coexist system call. Then you can also get back the running time in this structure. So there is just a place inside the kernel to save all the accounting information when the process just coexist and become a zombie process. Okay, so a zombie process represents two things. One is really a status of the process. Another is containing a bunch of information corresponding to that process. Okay, so this guy, now we are going to KO him. Okay, we can kill zombie. Okay, how to kill a zombie? Before that, I also talk about it. Yeah, the existing system call basically will go from the user space to the kernel space, and then this is something fake. Okay, that means that the process is still there, but the CPU never run it. Okay, now how about the wait system call? Last time we talked about the wait system call is having a mechanism that when you call the kernel code, okay, remember it's kernel code, your user code jump into the kernel code, and when you jump into the kernel code, kernel decide that, yeah, this is the moment that you cannot just return from a system call. Please stay there. Stay inside the kernel code for some time, until when? Until there is a signal that is generated by the zombie process before it becomes zombie, okay? Before it becomes zombie, there is a signal sent to that process, and the name for the signal, this is shorthand, okay? Why we use this shorthand later on, you will see I will use this as a constant inside the C program, okay? We call it sigchild, okay? Or child signal, child termination signal, okay? And this signal will fire to the parent only, to the parent only. So previous slides, you see that in a linked list of a task structure, you find there is a pointer pointing to the parent because we know there is a moment that we need the relationship, and the relationship is the moment that I die. I need to tell my mother that I died, okay? So follow that pointer, send that child signal to the parent. Now the parent knows, okay? Now it depends on the parent status. There are moments that the parent may not be, maybe he is so busy that, yeah, I don't care whether you die or not, okay? I later on handle you. That is the moment that the parent didn't call wait system call. Now, let's consider the scenario first. This is a more complex scenario. Is this parent has called a wait system call, and the wait system call is waiting for termination. So this is a signal to wake him up. Okay, so you can treat this. There is a alarm clock. Okay, then when alarm clock fire, then this guy wake up and do the following things. Let's take a look what are the things. First of all, before you call a wait system call, there is I don't know whether you have a program, a CPU, or I mean program CPU really mean using a assembly code. Okay, if you don't have the experience, that's okay. I want to introduce you something. Okay. By the way, how many of you have written JavaScript? Oh no. What happened? Yeah, in JavaScript, okay, there is a asynchronous mechanism, okay? You can install a function saying that, yeah, and when some events happen, please call that function with some parameters. We call it async. And the function callback mechanism, we call it just callback, okay? CPU also has this construction, is hiding inside the CPU. That is not about the CPU, but about a process. The same mechanism that you register for the service and wait for the service, and when the service is available or some signal is coming in, you will call a function to serve that signal or serve that guy. And here is the mechanism. The mechanism is there is a guy called signal handler. So what is handler? It's a function. Okay, you treat it as a function. If you have written JavaScript, it's also a function. Not just JavaScript, something like a Python or whatever, Ruby, okay? They all have this mechanism. Allows you to install a function. Now, although it is inside the kernel layer, it can be done everywhere. You hear me saying that Ruby, JavaScript, Python, they are all user level code, okay? And even running a browser, okay? So this is a very common mechanism that install. And what is the moment that you install it is when you call wait. When you call wait, you install a function inside the kernel, and what that function is doing, that function says when the kernel knows that, a child died, you send me a sick child, okay, then call this handler. So that means that there is a S here. You can receive different kind of signals, okay? It can be control C, it can be suspension, it can be segmentation fault, okay? This is an array of signal handlers. It so happened that this wait system call install one of it, okay? And the moment that you're being called that function is the sick child comes in. Now, after you install that function inside the kernel decides that, okay, you're ready because before you sleep you have to set the alarm clock, right? Here is the same mechanism. Before you sleep, you set the alarm clock, and alarm clock is set, good, you go to sleep. Now, for how long? Indefinite. No one knows when you wake up. Okay, there is no timeout. No timeout. That means that let's say if your mother don't wake you up, you will sleep for 8 hours. Okay, either one of the case happen, you wake up. No, here is not the case. It's indefinite sleep, sleep forever, until when? Until this sick child comes. Call that function. When you call the function, then I will wake up. Now let's fast forward. Fast forward to where? To this guy. Okay. So this guy, previously we have an illustration that this guy called exit system call. Now we fast forward that this guy calls exit system call and becomes a zombie. Okay, so we skip some step. Now when this guy becomes a zombie, before it do so, it will send a sick child from him to this parent. Okay, and the parent will know that, okay, there is a signal handler installed already for that specific signal. When the signal comes in, the function is called, and the function is a specialized routine that do something. And what are the things that you will execute inside this function? Very simple. You go to a function code, and the function code execute every one of it, and first of all, remove it, so that we know that, okay, you call that signal, okay, I handle it now. You don't do it indefinitely, because if I don't remove it, that means that the signal is still there. Remove that signal, we remove you, okay, what is that? The zombie. We remove the zombie process and take it away from the double list. Before you take it away, you will read all the details inside, okay? And in assignment 1, we will use this system call. Okay, so let's make it bigger. The system call is called, sorry, there's a 2 here. Hey, no, maybe move it with the Linux. Man 2 times. Yeah, the time system call. Get process time. So again, in assignment 1, we will use this. And there is a structure that you pass into the system call. And the system call can know for how long your process has run, for user time, for system time. Now, there is something more. This system call allows you to read the system time and the user time of your children as well. And this is why I said that previously the hollow body, there's no memory, no code, but a zombie. Why we hold that zombie? Because when you call wait system call, you collect every information. One of the information is the running time. You will put inside here. And when you call the system call, return it for you. Okay? So you will use this system call in assignment 1 in order to measure the execution time of your children. And you will understand some interesting property when you use it, but this system call is quite simple. I don't need to put it in a lecture. I will ask Kelvin to tell you what it is. Okay. Now, this is the moment that you collect the running time, you collect every information about this dead body. Okay. And I don't know where to store the source from where. And we move it from the W list. So this is the end of the zombie. And also, this is the end of the wait system call. Because this signal handler will also allow the process to continue to run the code after the wait. Okay? So this is the end. So I will return. Last few lectures, I never talk about there is a return value of the wait system call. Actually, the wait system has a return value. The return value is the process PID, okay, of the dead body, of that zombie that you have handled. Okay? Maybe this process, this parent has 11 children, okay? 11 children. I don't know which one died, okay? Then you can depend on the wait system call return value and know that who has died and who has been handled by you. Okay? So this is the return value. This is quite important. Okay, so this is about this game. This game now, you know that after this, the child process really die. Okay, it's gone. It's gone. We actually have another name for the wait system call. We call it very interesting. Okay, then we Google it. Wait system call. We call it Ripper. Okay. So do you know what is the meaning of Ripper? No. Okay. Yeah, somewhere I heard the name. Yeah. Just take away all the dead bodies. Okay? Just take away all the dead bodies. So wait system call is not just called wait system call, it's Ripper. Yeah. Okay. So this is the game so far, but it's only half of the game. Half of the game. So why is it half of the game? What happens if this guy dies, but this guy didn't call wait system call, right? There's another half of the game, and this is it. Okay, so make sure you understand this. Any question about this part? Half of the game only. No questions? Yeah, go on to the other half. Another half is quite easy. Okay, just something that I didn't say about it, and I just give you the knowledge. And the knowledge is, what happened if I didn't call wait system call, but the sixth child arrived at the parent process? What should you do? Okay, so inside the kernel, we actually do the following. Similar to case one, I skipped that animation actually. I was supposed to be this animated PPT, okay? The sixth child already attached to the process, okay? Just like here. At this moment, it's already attached to the process, but the process didn't want to handle it. Didn't want to handle it, just want to go on to something else, like this guy is doing some for loop, okay, and doing sorting, but never call wait system call, okay? So it just ignored the existence of the zombie until when? Until you call the wait system call. Then this attached signal will be handled. Once you install the signal handler will invoke immediately because the sixth child already have attached to the process. Okay? So no matter which scenario, the end result is two guys. End result number one is the wait system will eventually return. Okay? But you don't need to care when. Okay? Eventually it will return with second effect. There is no zombie process left. Okay? Now, this is the end of the wait story. And yeah, the short summary is that, there's a quite abnormal to see a zombie process. Okay? I never seen any process in a system that is classified as zombie because usually every parent will call wait. Later on, I will show you a program that process, okay, let's say a parent process, create a child and let the child die and not calling the waits. And what will happen if you do this? When you use PS, okay, so what is PS AUX? I heard from one of your senior classmate from IE, okay? She is supposed to be she, okay? she tell me the following while she is going to the interview, okay, interview for a job, okay. The first problem is, ask her what is this command, PSAUX, okay. So what's PSAUX? Very useful command. Now I type, and what are they? Okay, so I go to the first row so that you can see what is going on. Okay, first row is here. Okay, first row, so PSAUX. So it's actually showing you the entire system activity. What are the processes is running inside the system? This is the number one PID, and the command is like that, when it's stored, blah, 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 okay. And this is the system process status of the entire Linux, and it's PSAUX. Now, let's take a look what is the thing that I want to execute. PSAUX pipe grab, so what is pipe grab? Means that I will ship all the standard input, standard output, ship all the standard output to be the input of the grab program. So that means that I ask the grab to process the output of PSAUX, and what is going on next is I want to grab means to look for some text. The text is called defunct. Okay, so defunction means no function. Okay, so let me check whether I have a zombie process in my system. PSAUX pipe grab defunct. Suppose no. Okay, what is the output here? The output is the process that I call grab. Okay, grab that defunct guy. Okay, is actually a process, so let's find out this process. But there is no other process carrying the name defunct. Now, what is the meaning of defunct? Defunct means a zombie. Okay, so this guy is a zombie. If you have a defunct tag after the PSAUX output. Now, how can we effectively generate a zombie process? Let's see. This is the program that effectively generating process, which will be zombie after it's executed. Now, give it some time. Now, first of all, what is this line? This line I make it a little bit complicated. Okay, you can treat it as just a get char. Okay, if you really want to understand what this line means that no matter how many characters you type, okay, you type a very long list of characters, I will process it one by one until I get new line character and get out of the loop. So if I'm obedient, I'm a good guy. After you call the get char, say that what I say, look at the status of blah blah blah, and you just press enter. That is equivalent to calling one get char only. Okay, so I love to do this. By the way, this semicolon here means an empty loop body. Okay, so look at this program. Tell me which part is the parent, which part is the child. I give it 1 minute. One more thing. I start with some easy program, right? Now this program has a lot of shorthand, okay? This if statement, do you know what this if statement is doing?
Only parent process.
Yes, but why I can write in this way? I didn't write anything wrong. I'm not doing comparison equal. I make it on purpose with one equal sign. Do you know what I'm doing? What? First of all, after this call, we will assign any value to PID. Yes, I will assign some value to PID. Okay, but why I write it this way? Give it 1 minute to understand the program first. Many C programmers love to write in that way and pretend to be very smart. Pretend. Okay, I will show the same program now. Don't worry. Just here. Zombie.c. Okay, so it's the same program. I should make wider. Maybe I deleted the comment. Okay. Oh, yeah, that is easier to read. Okay, so the previous if statement is actually equivalent to this guy. Okay, is it? Yeah. This equal sign actually is an assignment statement. Assignment statement will generate return value, and the return value generated by assignment statement is the value that you just assigned. Okay, so when false returns 0 and you assign 0 to PID, the assignment statement, assignment operator or the statement itself generates 0 as well. If the fault return 1, 2, 3, 4, it will return 1, 2, 3, 4 after an assignment statement. Okay, so the assignment statement is generating return value. It is a very common practice on nearly all languages. Okay, so as our classmate mentioned, this code is very clear now. Only child or parent will execute this body, right? Who? Child or parent? Parent. Parent get the return value of non-zero. So the parent will execute the if body. How about the child? Where is it? When the program just run, I hit enter after I type dot slash blah blah blah, okay? It dies immediately, right? When you call for, the child don't execute the if body and dies immediately. Now, what happened after the child dies, right? When the child dies, it means that it will become zombie. Now you understand it will become zombie. Now I use a get child here so that I can block the parent process, and before it block, whether he execute with system call is the main point, right? Look at the code. I never call waste before I call the first layer of the get child, and the second layer of get child I call waste. Now you can see a difference. So make sure everybody have seen this clearly, and remember that there's two get child waiting for me. The first get child, I expect that I will find a zombie. Second get child, I expect that I cannot find any zombie. Okay? So that's good. Okay, compile. Let's go. So my program run, and the return value here, look at the status of this process 4054. Okay, means the child process. Okay. No. I use the hotkey of Mac. Okay, so bigger. Too big. It's too small. Hey, come on. I always use the wrong hotkey. Okay, so let's do it. Look at the process for grab 4054. So what I'm typing here, the command that I just typed, highlight here, is meaning that I will grab every entries from the process status report containing the number 4054. Okay, and enter. Yeah, this is not wide enough. Wider. Execute again. So what can you say about the process 4054 highlighted in red? What can you say about this? Take a look at the end of it. There is a tag called defunct. Okay, this means that that process is reflected using the process viewer, process explorer, because PS will dump all the process status out. I call it process status. And it's being found that it's defunct, so it is a zombie process, and the zombie really exists until when? Only up to the moment that I hit enter. When I hit enter, what will happen? When I hit enter, I will get past this while loop, and then call waits. And I say, look again. Look again means that you type that PS again, and then you will find that zombie removed. Now let's go. Enter. So look again. Grab again. Can you see the new report? Can you contrast with the new report and old report that the zombie process, although I call the executable name zombie, okay? This doesn't mean that, oh, you call it zombie, then it becomes zombie immediately. No, okay? Yeah. It's so happen I call it zombie. Now, it's removed. But how about the parent process? The parent process just call the wait PID, wait, okay, wait system call. I can modify the bit. I modify the program a bit by printing the return value of the wait PID. Okay, return from wait equal to, and you will see the results. Okay, compile. I will show you the code, don't worry. Okay, run for the first time. Now this time the PIDs change. Okay, become this number 6. Okay, so still the same effects. Okay, before I hit the first enter. Now I hit the first enter. Now move down, enter. So it says the return value of the wait system call is so happen to be this guy. So because I only have one child, and the child PID is that number, so I didn't lie to you. The wait PID return value is the PID of your child. Now execute again, still the same, right? The zombie is gone. The zombie already removed by the wait system call. Okay, so that means what? That means the entire system, like the shell, maybe other system, a part like SSH. Okay, SSH actually create many tiles. Okay, it's all implemented in this way. It will call wait system call and wait for child termination, so that in the entire system you won't find any zombie left. Now, what is the effect if I allow there are zombies in the system? Okay, and I do it deliberately. I do it on purpose. And what is the end result? That's why I bring this computer here. Okay, I don't want my Mac full of zombie. Okay, yeah, I will make this guy full of zombie. You're welcome to do the same thing in Apple Store. Okay, so first of all, what is the damage that will bring about if you cause too many zombies in the system? Okay. You know, there is limited resource in the computer, the RAM, the hard disk, the power, the battery, all are limited. But there is one seems to be harmless guy, but that harmless guy is also limited, is the PID itself. Okay, PID is limited. You use up the PID. Okay, and I don't know who designed it. Okay, look at this number. Look at this command. So what is this command? This command is kind of interesting. This is the first time I show you this directory. Okay, this directory only exists in Solaris and Linux. Mac don't have this directory. Okay, so what is this directory? Let's go there to take a look. Okay, so I can CD actually. You can do the same thing with me if you're using Linux and LS. You'll find a bunch of numbers here. So what are they? Actually, we call it a pseudo file system, a false file system. This file system is crazy, really crazy. Every directory is actually the running process, a running process. When you CD to that running process, okay, I can do the following. Let's say I use this terminal, okay, to execute the zombie process again. I guess, so happens to be a nice number, 4096, okay, 4K, yeah. This is the zombie child. I guess the zombie parent is 4095, right? Usually it's like that. And in this directory, okay, actually it's a export of every data inside the kernel, okay. I can CD to 4095. No problem. I go in, LS. I see something. I don't know what it is. Okay. Now I tell you something interesting. Let's say, what is the command line? Okay. We can cat command line. Okay. And you will know the command line to call this process or the current code it is running. for every process. That means that this directory contains all the necessary information for you to look into the process. Okay, it doesn't matter. Let me go back to one layer. So I'm still in this layer. And look at the code, the file, okay, not the code. The file that I asked you to look at it. And this file system also export other things. Under the SYS directory, it is a system setting. And system setting here means the PID, the maximum number allowed in the kernel. Let's take a look. Okay, copy, and then I don't need to copy it, just type. Okay, I can do this. Read it. Read what? The system configuration of the kernel PID maximum value. What happens if I create enough number of processes so that I use up this value? What can you think of? What can you guess, okay, if I use up this value? Let's say I create infinite number of processes while one fork and use up this value, then this while one fork cannot generate other processes, right? How about the normal usage of the system? That's why I bring this computer here. Okay? Because usually the end result is either it's very hard to control C to terminate all the process, or you have to reboot the process. Okay? And I will execute this code first. Okay? So what can you say about this code? I give you some time. I first have to set up this computer. What can you say about this code? Why this code is we call it an infinite zombie factory. Yeah? Why is that? But in the meantime, I have to stop the recording because I have to switch the display.